next place to
Yeah, I just want to have like a good place to film. So that
That's good.
I don't want to like hang out.
Yeah. All right. Are we good?
Oh, wow, this is being filmed in Southeastern Union.
Airtime, you know when you're good.
Yeah, I think it's good.
Last class we covered the Toshin theorem, and that's a big generalization of Fermat's law theorem, which states that a to the p minus 1 is congruent to 1 mod p, where p is prime and a and p are relatively coprime. You might recognize the Toshin function from last class. So this is the big generalization by Euler. And then this is what we're going to be proving today. So Fermat's little theorem states that a to the p minus 1 is congruent to 1 mod p. Okay. And at the end, you can just write Wilson's theorem down in your notes. We're going to be proving that next class. Okay. Before we start with our proof, I want you guys to notice the homework because it's kind of related to everything. Basically, we covered a lot of mod properties last time, if you remember. You can multiply, add, and subtract, and do all that. But the one big no-no up with mod is that you can't divide necessarily for all cases. If, let's say, you have 10 is congruent to 4 mod 6. Right? If I divide both sides by 2, you'd yield that 5 is congruent to 2 mod 6, but clearly that's not true because 5 is congruent to 5 mod 6, right? So basically you can only divide in mod if the number you're dividing by, the factor k, is relatively coprime to the mod that you're in. So, but look at the homework. It says AK is congruent to BK mod n. You can only divide both sides and have a true congruence if and only if GCD of K and N is congruent to 1. That means K and N are coprime. Okay? So keep this in mind. Yeah. Let's start with the proof. This, you should start your notes from here. All right. Consider the residual set S from 1 that contains all the integers from 1 to p minus 1. Okay. These are the residuals in mod p. What does that mean? That means for any integer out there, if you were to put that modulo p, it's going to be one of those numbers, right? Think about like in mod 5, right? In mod 5, an integer can either be 1 mod 5, 2 mod 5, 3 mod 5, 4 mod 5, and that's it. Can it be 5 mod 5? No, because if it's 5 mod 5, then that just means 0 mod 5. It's congruent. It's divisible by 5. These are the 4 options. 1, 2, all the way down to p minus 1. So thus we have defined S as the residual set in modulo p. Now what else? By definition then, if you take any of these numbers, mod p, it's just going to be that. 1 mod p is 1, 2 mod p is 2, all the way down to p minus 1 mod p is going to be p, because it's less than p. Okay, now,
just remember this.
multiplying S by A and A mod here, actually, right? We're trying to prove A. multiplying the set S by A yields what? Yields AS, which is gonna include A, 2A, all the way down to what? Multiplying A that times this, A times this, all the way down to, A times P minus 1. Okay. If I were to, here's a side note before we prove anything. If I were to find the product of all the elements of AS, what would I get? So you're multiplying A times 2A times 3A all the way down to A times P minus 1. Think this. Get it in the form of A to the P minus 1 times something. How many A's are there going to be first? Exactly. So there's going to be P minus 1 A's, right? So A to the P minus 1, and then times 1 times 2 times 3 times 4 all the way down to P minus 1, which is just P minus 1 factorial. Okay. So I'll write this aside. Okay. Now, what we need to do is here's the thing that we're trying to show is that we need to show that when you multiply this out, you get this, right? Now we're just trying to find what is this going to be congruent to mod P. Okay. Every one of these integers, A to A all the way down to A times P minus 1. Like the residues, each one of these is either going to be, let's say, any one of these, let's call them AS, right? ASI mod P is going to be congruent to the integer, say X, from 1 to P. What this means is that for each one of these, the residual is, when you divide by P, just like any number, it's either going to be, it's going to be one of the numbers from 1 to P minus 1, right? Why is that? Because A doesn't divide P, and none of these numbers, these small numbers, divide P. So the residuals, when you take A mod P, A is congruent to some integer, let's say A1, okay, mod P. 2A is congruent to A2 mod P. All the A1s, all the AIs are going to be in between 1 and what? P minus 1, right? They can never be P minus 1 or greater. Just like the residuals. Okay. Any questions so far? No?
Yep, no questions. Continue.
Okay. So my goal right now is actually going to be to try to prove that each one of the residuals is distinct. And why that's important, you guys are going to see later, but let's just prove that, and I'm going to show you why it's going to be really important. And then it's good. It's pretty brilliant. Okay. Let's say, for sake of contradiction, remember class number 1, favorite proof style is contradiction. So for sake of contradiction, assume two or more elements in the set AS, so in above set, are congruent mod. So that means, like, let's say 2A is congruent to, 4A mod B, something like that. Okay. Let's say the two numbers in the set that are congruent are NA and MA. Let N be, either 1, 2, 3, whatever, and M be one of those other integers. N and M are different, and let's just say, without lost generality, that M is strictly greater than N. What would this mean? Well, that would mean that MA is congruent to NA mod P. And then MA minus NA is congruent to 0 mod P. When something's congruent to 0 mod P, that means MA minus NA is a, what is that? That means this is divisible by P. That means P divides MA minus NA. Okay. Some algebra, some factoring, we see that P divides M minus N times A. Now we know P doesn't divide A by our initial claims, which is that A and P are relatively coprime. So that means M minus N must be divisible by P. But M minus N can't even exceed P minus 1. What I mean by that is, can M minus N ever be greater than P? Right? Let's say there are 6 numbers. Let's say the set has A, 2A, 3A, 4A, 5A, and 6A. And that means this is mod 7. Can any coefficients, when you subtract them, be greater than 7? No, they won't even be greater than 7 minus 2, right? Even if you take the biggest coefficient 6 minus the smallest coefficient 1, you'll get 6 minus 1 equals 5, right? Which is, of course, less than 7. So M minus N, where M and N are distinct coefficients in the set, it can never exceed P. So that means we know for a fact that this cannot be valid. P cannot divide M minus N times A. So that's basically the whole proof. We have concluded that with contradiction, that the above statement can't be true. For the sake of contradiction, assume that 2 or more elements of the above set are congruent mod P. They all must be distinct. They all must have distinct residuals in modulus P. And just for you guys to get a more intuition on that, let's say, like, again, P, let's just go with P equals 6. Let's say that if this was like 2, none of the other ones can be 2. Residual can be equal to. Let's say this was 1, none of the other can be 1. and so on. You fill this out, whatever. And all these numbers are going to be distinct, the residuals. And by residuals, I mean what are they congruent mod p? Okay, what's the remainder? Okay. So all of these are going to have distinct residuals, just like this set, just like the set of residuals. That means, well, when you divide it by p, when you divide all these by p, if you take the mod p of this set, it's going to yield this set. It's going to be just a different permutation of that. So they're all going to be distinct. And of course, all the residuals are going to be between 1 and p minus 1. Say residuals are. So R1, R2, R3, all the way down to RA, or p minus 1. All of them are going to be distinct. And they're all going to be this exact same set, but of course, maybe not in this order. Just a different permutation. Okay. It's a lot of words, a lot of jargon, but what is the point of all this? What I'm trying to tell you is that when you multiply all these together and you take the mod p of it, what's going to happen? Well, it's going to be, we're trying to find out what this is, right? So a to the p minus 1 times p minus 1 factorial is the product of all of them. In mod p, what that's going to look like is, well, we've already decided that the residuals are going to be R1 all the way down, which is the same as this set. So what I'm trying to convince to you is that when you multiply them, it's going to be the exact same as taking the product of these. And what's the product of 1 all the way down to p minus 1? Just p minus 1 factorial, right? P minus 1. So because this set and this set are congruent mod p, that means when you multiply this in mod p, you're going to get this. When you multiply this in mod p, you're going to get the same thing, which is p minus 1 factorial. Okay? Now, p minus 1 factorial, because none of those integers in p minus, when you multiply 1 times 2 times all the way down to p minus 1, right? When you multiply that, none of these numbers are going to divide p because p is prime. That means p minus 1 factorial and p are relatively co-prime, which means we can, in this case, divide both sides. And then we're left with a to the p minus 1 is congruent to 1 mod p. So thus we've proved Fermat's law theorem. This was probably our most challenging proof till date. So I know some of you have questions.
What was that last step?
You said 1 mod p is the answer?
I just derived.
Yeah,
So
to
p minus 1,
is congruent to 1 mod p.
what was the question?
I'm sorry.
Before you got to the, so where'd
This.
you get to the, yeah, so where'd you get to the p minus 1 factorial on the right side?
Okay, so basically the residuals, we've shown that because they're all distinct, right? And so they're all distinct residuals. They're all going to be different, mod p. And you only have p minus 1 things to choose from, right? Basically, the residuals when you take mod p of this set, the residuals R1 are this set, this R set, is the exact same as this set. It just doesn't have to be necessarily in that order.
I got you.
And then so when you multiply them all out, you get that they're congruent in mod p. So yeah. Somewhat, yeah. As long as you have if you comprehended even a little bit of it, that's fine because you have a week to really solidify it. And then there's always videos you can watch online, or you could watch the lecture recording. But
Question for you with, Vermont's theorem here, how, would you rather know the theorem or would you rather know the process to get, I mean, obviously, for me to hear was important, but
Yes.
what are you gonna use it to,
Yeah, so in competition, just like we did last time when we were just introducing it, when we introduced Euler's totient, it's really useful in competition math, but of course there's none of the competition at least that we do, the AMCs or any of our local comps, there's no proofs in them. It's just straight problem solving. So just knowing the theorem is going to be really important. Basically, the whole point of this, at least in terms of their use case in comp math, is that, again, like last time, getting to 1 on the right side of your congruence is really beneficial. Because you could do some like crazy, if you ever notice, like if you recognize what's the remainder when you divide like some outrageously large power, like 6 to the,
2025.
2025 is gonna, when you divide it by, I don't know, like 7, what's the remainder gonna be? Something like that is gonna be, it's gonna be a lot easier if you get to 1, because we could try doing this, I guess, because 6 and 7 are are relatively co-prime. Yeah. Yeah. So 6. Okay. So by the Fermat's theorem, 6 to the 5, right? 6 to the 7, or actually 6 to the 7 minus 1 is going to be congruent to what? 1 mod 7, right? So I mean 6 to the 6 is congruent to 1 mod 7. And then to get to 6 to 2025, well, you can just, you could get this all the way up to whatever, what that be. So yeah, you can multiply this, or you could raise it to the power of 337 on both sides, and that yields like 18 minus, so 7 into 1 mod 7, and then now you only have to multiply, that you don't have to multiply as much. So, or it's gonna, it's gonna be, I did that wrong, but sorry, 2022. There we go. Yeah, it's gonna be congruent to 1 mod 7. And then from here, you can just multiply both sides by 6 to the 3, because that's a remainder. And then that's going to be your, and then you continue the thing, and then you can get your answer pretty easy from there. But yeah, getting to 1 is just going to be really, really, really beneficial for you. So, yeah. Any questions on the proof itself for today? There should be a glaring, yeah. Did anybody say that?
Sorry, I was going to say no further questions.
No further questions? Okay, but you should have one pretty glaring question is why can you divide it only in the case where the factor is relatively coprime to the modulus? That's what your challenge is going to be. Try to just brainstorm with your group, and then for homework, if you could formalize a good proof for that, that'd be great. If you get really stuck, you can't always look it up, but it's gonna be a lot better for you if you try to do it by yourself. Okay, and then the last thing I want you guys to write down is Wilson's theorem, which is already printed up top over there. And then yeah. Just give me a thumbs up when you have that written down. I'll have that up if you haven't. Okay. It's the end of lecture, then you guys can start. What time is it? We have a good amount of time left. Spend a little bit of time doing that, and then we're gonna finalize some leadership positions for the rest of class. If you, who has like a picture of? Did you take a picture of like
Of the homework?
of the board?
Oh, I took a picture of the board as well. but
Okay, yeah. If you
can
could
use
send
it.
that in the group chat.
You can use it if you like.
Okay. And then
Don't worry, I'll send it. I'll just go.
there's like
the
a.
rest for the rest.
We could make a prove it group chat if you guys want.